In this video, we're going to look at analyzing functions by looking at their graphs and applying some other techniques. And this first example we're looking at here of a rational function, I already have the equation typed in the Desmos and we're looking at it, and we kind of have a long list of things that we're looking for in order to find. And we're starting with trying to determine the domain of this. Now, graphically, if I'm looking at the graph function, one of the first things that I do is I start scanning from left to right and looking for breaks. And we see that there are two breaks in this function. There's a break at x equals -1, and there's a break at x equals +1. And a way we could tell it's actually much quicker is if you have a rational function, factor the denominator. Once you have the denominator factored, you can look, and any value of x that makes the denominator 0 has to be excluded because division by 0 is undefined. So looking at that, we know that x cannot equal 1 and x cannot equal -1. And graphically we look, and that's where the breaks are. So our domain would be the set of all real numbers excluding those values. So -∞ to -1. -1 to 1, 1 to infinity. Now, the range is next. So range, we're looking at the graph vertically. And so if I change my zoom and I zoom out, I look and I see that the bottom of the graph is getting very flat. And I try to determine, well, where is it getting flat at on the graph? What y value? And it starts getting flat around -1. And in fact, it's never actually going to get there to -1. It gets very close, but it won't actually get to -1. And so when we're scanning the graph, we also see that the function decreases without bounds. So all values less than -1 are going to be accounted for. So we'll go from -∞ up to -1, not inclusive on the -1. And then there's a gap that happens where there's no y values accounted for that we see until we get to 0, and then we have the parabola looking part where both sides in between those vertical asymptotes are increasing without bound. So it goes from 0, and since it equals 0, we include it, and keeps increasing to infinity. Now our intercepts, the graph only crosses the x and the y-axis at the origin, so both the x-intercept and the y-intercept, 0, 0. So technically, the origin is the intersection of both axes. Now we're looking for where's the graph positive or negative. All right, so a graph is positive where it lies above the x-axis. The purple region here, it's kind of a little hard to tell, but the purple region is where the graph is positive, lies above the x-axis, and all the blue is where it lies below. Now here's one thing to consider when you're writing your positive intervals, because it would look like just that section of the graph that lies between -1 and +1 would be our interval. However, that would be incorrect because 0 is neither negative nor positive. So I'd have to break that interval at 0 for my positive interval. And the graph is going to be negative everywhere else. So it's negative on both the left and the right sides of that section there. So our negative interval would go from -∞ to -1, and then to the right side of the asymptote at 1, 1 to infinity. Now, relative extrema, we're looking for turning points of the graph. There is a turning point at the graph right there at the origin, a relative minimum. So I'll say minimum at 0, 0. Okay? Now we'll look at decreasing and increasing intervals, and we'll start with the increasing part of the graph. So remember that a graph is increasing where it has positive slope. So as it goes to the right, it is going to be going up. So our increasing intervals on our graph here will be this right-hand section, because the entire right-hand side, as you go to the right, the y values are increasing. So our increasing intervals would go from 0. I got to exclude 0 because 0 is neither increasing or decreasing. 0 to 1 and 1 to infinity. And everywhere else that is not colored, so what's left in blue, would be considered decreasing. So we'd go from negative infinity to negative 1, and then negative 1 to 0. Now let's look at concavity. So concave up is where the function has curvature, where it would bend upward. And in fact, there's a much more complicated way to describe that. It's when the slope of the curve is increasing. But you think it's concave up is like a cup, and concave down is curved down like a frown. Well, I changed the colors in the sections of the graph, and the green section is where it's concaved up, curved upward. This interval would go from negative 1 to positive 1. The intervals where it is concave down is everywhere else in blue. So go from negative infinity to negative 1, and then from 1 to infinity. Now we'll look at discontinuities. Well, discontinuities are simply x values that had to be taken out of our domain where we had breaks in our graphs. And we go back and we look at the very beginning of the problem. The discontinuities that we had to exclude here were negative 1 and positive 1. So our discontinuities, and we'll label the kind of discontinuities we have. And we have vertical asymptotes of both. So I'm going to abbreviate vertical asymptotes at x equals negative 1 and x equals positive 1. Now, we can also identify there's other kinds of asymptotes that are not necessarily discontinuities, and that would be a horizontal asymptote. And here in this graph, I have the horizontal asymptote display. It is the y value that the graph is flattening out at that the graph gets very close to, but in this case it doesn't actually equal that value. And we look here, and that is at y equals negative 1. So we have vertical asymptotes at x equals positive or negative 1, and we have a horizontal asymptote at y equals negative 1. And then we'll do our end behavior. So the end behavior here, we're trying to describe what is the graph doing as you approach the ends of your domains. And in our class, we describe this behavior using limit notation. And so limit notation, we're going to say the limit as x heads towards the left side of the domain. Well, the left side of our domain interval was negative infinity. So as x heads towards negative infinity, basically saying as x is decreasing without bound, our function here, I'm going to write f of x, is equaling, well, what are the y values doing as my x values decrease without bound? Well, as I go to the left, my y values approach negative 1. So this limit, we say, equals negative 1. And now we're going to do the right side. So the right side here, which would be the limit as x heads towards the right part of our domain interval. So the far right is positive infinity. So as x increases in value without bound, our function of x is, well, we go look at our graph, and it's leveling out at a y value of negative 1. All right, let's look at another example of trying to perform a graphical analysis of a function. And so I already have this equation typed in here on Desmos on the right-hand side, and we look at this graph, and it has a break in it, and it looks like the only break is at 3. So we're like, well, okay, well, x cannot equal 3. Now, the only way to be sure that that is the only discontinuity that exists in this graph for a rational function is to actually factor out the denominator. So we're going to factor this denominator. It's going to make x minus 3. So that gives us the vertical asymptote at 3. And then we also have x minus 1. So there's actually two numbers we have to exclude out of our domain interval, positive 3 and positive 1. Now when you're doing this stuff and finding the domain, you don't want to cancel anything out. I don't want to cancel out the x minus 1s. and simplify the problem because that removed a discontinuity. So I'm going to go ahead and write the domain interval right now. It's a set of all real numbers, excluding those two discontinuities. So negative infinity to 1, 1 to 3, and 3 to infinity. Now, the range here, the range would appear to be going from negative infinity to 0, and then 0 and above, but we have an issue. The issue is what is going on at 1. Well, we come in here to Desmos, we try to figure out, well, we don't really see anything special about 1. We start tracing here, and we get the 1, and it says undefined. 1 undefined. I can't really hold it there, but there it is. So we have a hole at 1. So whatever that y value is supposed to be there, we would have to make sure it's excluded. Well, we're able to tell for this one that that y value of that hole is actually at negative 0.5, because both sides are getting very close to negative 1/2. So it's right in between there. So our range would go from negative infinity, and then I have to exclude that hole there at negative 0.5. And then we go from negative 0.5 to 0. So we got that whole left side accounted for, and then the right side of this graph goes from 0 to infinity. All right, our intercepts. Well, graphically, this graph does not cross the x-axis at all. So we have no x-intercepts. Our y-intercept here is at 0, negative 1/3. And now we want to do our positive and negative intervals. Well, our positive interval is going to be everywhere where the graph lies above the x-axis. So let me change the color of that piece, and we look. The one section that lies above the x-axis is the right-hand side of that graph, which the interval would be all those x values that's within there, which means that we're going to go from 3 to infinity. The graph lies above the x-axis. And we're negative everywhere else, which would be that whole black section there that I didn't color. So our negative interval would go from, it'd be the rest of our domain, negative infinity to 1. And then negative infinity to 1, and then 1 to 3. Now, relative extrema. I'm looking for turning points. I'm looking for a maximum or a minimum, and I don't see a maximum or a minimum in this graph. So we'll say there's no relative extrema. Increasing and decreasing intervals. Looking at the graph to find an increasing interval, you're trying to determine where's the graph going up as you go to the right. Well, the entire time you trace along this graph from left to right, you are going to be decreasing in value. So there are no increasing intervals. And the graph here is actually always decreasing. And so what I would do is write the entire domain interval. It's decreasing on its entire domain. So negative infinity to 1, 1 to 3, 3 to infinity. Now let's determine intervals for concavity. So the function is going to be concave up where it has an upward curvature on it. And I have that highlighted right here on the right-hand side. The right-hand side has a curvature where the inside of the curve is pointed more upward. So that is going to be where it's concave up. So this graph is going to be concave up from 3 to infinity. And it's going to be concave down on the entire left-hand side here. And I got to remember to exclude that value of the hole because the graph doesn't exist there. So negative infinity to 1, 1 to 3. Our discontinuities are next. And so when we factored this function at the very beginning to figure out the x values we had to eliminate, we saw we had to eliminate the x value of 3, and we had to eliminate the x value of 1. And anytime you have to eliminate an x value from the insides of the domain interval, those are considered discontinuities. And we're just going to label the kind. So we had a vertical asymptote, I'm going to abbreviate, and that was at the discontinuity that lies at x equals 3. And we have a hole, that's a discontinuity, at x equals 1. And we already found what the y value is. If we wanted to write that as a coordinate, that hole is actually at 1, -0.5. Now, when we're talking about all of our asymptotes, we have to also account for the horizontal asymptote that exists here. And we see that the graph flattens out on the x-axis, so we'll identify that we had that vertical asymptote, and we also have a horizontal asymptote at y equals 0. Now we'll talk about the end behavior. So the end behavior is what's the graph doing as your x values head towards the ends of their domains? Well, we're going to describe this kind of behavior using limits. So the limit as x heads towards, let's start with the left side. So looking at my overall domain interval, the left side is -infinity. So the limit as x heads towards -infinity for this function of x. So basically what this limit equals is what are the y values getting close to as you head that direction. Well, as I go way off to the left, I'm looking, the graph, it gets very close in y values to y equals 0. So that's what we set this limit equal to. And then we repeat all those steps for the right hand side. So the limit as x heads towards, I go back to my domain interval. The far right side of the domain interval is infinity. So as x is increasing without bound, the function of x, which are your y values, what are your y values doing? My y values inch their way closer and closer to the y value of 0.